Alright gang, welcome back to the regression series here on zedstatistics with some new intro music to keep it fresh. My name's Justin Zeltzer and this is the fourth video of 5 in the series. And today we're dealing with functional form and transformations. Now I've said fourth video of 5, but I've decided that there's a lot of content to deliver for this one, so I've split it up into 3 bite-sized chunks. So there are 3 separate videos here, but they all lead on from each other and deal with the same data set, which we'll meet in just a bit. But first, let's have a look at what each of these bite-sized chunks contain. In the first part, we'll be dealing with numerical variables, like we have in previous regression videos here, but we'll be looking specifically at non-linear relationships. So where, say, the y and x variables might exhibit squared relationships, maybe an inverse relationship, and we'll also be looking at something called logarithms or logs, which will be crucial for you in your study of regression because they're just used bloody everywhere. In part B, we'll be dealing with categorical x variables. So these are yes-no type variables, male, female, or for another example, what about ethnicity? How are you going to model ethnicity in a regression? How do we turn this categorical information into something numerical that could be used in a model which is still mathematical? Well, we'll be answering those questions in part B, as well as looking at this infamous dummy variable trap. And we're also going to have a look at interaction variables, or you might also know these as effect modifiers. And even though interaction variables could also be numerical, they're probably most easily illustrated using categorical variables. So I'm kind of putting them under this heading for the purpose of keeping things simple. And in part C, we're going to see what happens when our y variable, our dependent variable, is categorical. So for example, imagine trying to model whether or not I'm going to pass this statistics exam or not. If that's our y variable, how do we deal with that? Well, there's actually a host of ways of doing so, and they're all under the umbrella of something called discrete choice modeling. But here we're going to deal with just one of these types of models called logit models, which are also known as logistic models. Now, as I said, each of these 3 parts are going to be using the same data set. And I'll introduce that to you right now. It is Jaybob's used car sales, which is actually a data set I've created myself just so things work out quite nicely for illustrative purposes. You can download the dataset and play around with it yourself. It's just in jaybob.csv, which is a file I've linked to in the description of this video. And I'll also put a link to an Excel file that houses all of the models that I've used in the video as well, so you can check up to see any of the extended output that maybe I've left out. Nonetheless, hopefully this will explain why we have a little car graphic down here in the bottom right-hand corner. But the variables of interest today are going to be price, which is the advertised sale price of the car in Australian dollars, please. The age of the car, which is counted in years. The odometer reading, which is in thousands of kilometers. A variable called pink slip, which is the presence of a roadworthiness certificate, and that's coded 1 for yes and 0 for no. And then we have a variable called sold, which is an indicator variable illustrating whether the car has sold or not, 1 being yes and 0 being no again. So if you open up jaybob.csv, you'll see that the data looks a little bit like this. We have a car ID column, which obviously doesn't enter any of our models, but it's just there to help us identify which row is which. You can see there's a decent variation in price, age, and odometer. Those are our numerical variables, and yes, our categorical variables here. So this video is going to progress by me presenting to you a suite of models, but we're going to start with the simplest model we can think of for the moment to try to explain the sale price of a car, and we're going to use both age and odometer as our independent variables. Now, if you're unfamiliar with how this works, I would suggest you watch the third regression video, that's regression 3, which goes through how to interpret regression output. So I'm going to take that as read for this video. And another point to note is that I'm using Microsoft Excel, so I'm not using some fancy software to run my regressions. I'm using something you can use yourself if you have Microsoft Excel, And all you need to do to run a regression is to go to this Data tab and go over to Data Analysis, which is way over on the right-hand side over here. Once you click that, you can scroll down to where it says Regression in the Analysis Tools, and you'll get a little window that looks a little bit like this. You've got an input Y range, which I've already pre-filled here, but you can have a go at doing this yourself. You basically just select the data for Y and the data for X, and I've included the headings in both of those cell ranges, so I'm going to have to tick the box that says Labels, and then you can select to put it in a new worksheet, the output, that is. And it will look a little bit like this. Well, this is part of the output that's going to be most relevant to us now. We've got the dependent variable, which is price, and here we have the coefficients, the standard errors, the t-stats, and the p-values. So we can put this all into a sample regression equation, which is 4,615.9. That's our intercept term. We've got the coefficient of age, which is 98.9, and the coefficient of odometer, which is negative 23.0. And our R squared here is 0.17, so that's not particularly high. If you're not quite sure what that means, I would suggest watching videos 1 and 2 because I deal with R squared quite a lot in those first two videos. But just to start us off, let's interpret what these coefficients actually mean for age and for odometer. So here it says that for every additional year in age, the car can be expected to increase in price by $98.92, that's this here, on average, holding odometer constant. Now, that already might be rubbing you the wrong way, because I imagine you'd think that for an older car, you'd expect a price that's a bit lower than the newer cars, right? So as age increases, you would expect the price to go down, which is not what's being shown here. So that might be your first indication that something is not quite right with this model. But let's just hold that over for the moment. Let's interpret what the coefficient of odometer means. This tells us that for every additional 1,000 kilometers on the odometer, because don't forget this variable is provided in thousands, the price is expected to decrease by $23.03 on average, in this case holding age constant. So what we've done here is that we've presumed that the relationship between price and age and the relationship between price and odometer are both linear. But something perhaps we could have done before putting this model together is actually checking the scatter plots where we compare both bivariate relationships. So here's advertised sale price versus age. So these are all of the, I think there's 100 cars in this data set. And you can see here that we've got a scatter which is not necessarily lining up in a linear way. So what the regression we've conducted is trying to do to this is fit a straight line through this scatter of data points. Now, can you draw a straight line through this that makes sense? I don't think you can. It seems to me that there's a bit of a curve situation going on. And let's have a look at odometer. Again, we're trying to draw a straight line through this haze of data points. And one might argue that it might be more appropriate to draw some kind of curve here. So while maybe for age we could have some parabolic relationship, so this could be a sort of squared relationship, for odometer it seems to be some kind of inverse relationship. It might have this sort of asymptotic relationship. So let's say we model this relationship between price and these variables like so. Price is a function of age and age squared, and it's also a function of the inverse of odometer. So in that way, by doing this, we'll be allowing the model to, instead of drawing a line of best fit through this, we're kind of drawing a curve through this one, a nice parabolic curve through age, and some kind of hyperbola type thing through odometer. Now be aware that this is still called a linear regression. So the phrase linear regression refers to the coefficients themselves. So this is linear in the coefficients. Price is regressed linearly against age. It's regressed linearly against age squared. And it's regressed linearly against 1 on odometer. What I mean by that is that to get these variables for model 2, what we're going to have to do is take our age variable and we square it to create age squared. And we can take our odometer variable and we can inverse it to create 1 on odometer. Now what happens then is that we're going to just put these variables, the age squared and 1 on odometer variables, into our regression model, and Excel won't know that these are non-linear variables. It'll just treat them like a linear variable. Now a common question might be asked here, if we're going to include age as a squared variable, why do we have to include the linear version of age? Well, that just allows us the flexibility to move this parabola away from the y-axis. So I'll just go back a bit. You can see this parabola we want to draw has a base which is not at the y-axis. The base will be somewhere around, say, 35 or so. So to allow us the flexibility to shift the base of the parabola away from the y-axis, we're going to need the age to the power of 1 variable there as well. Anyway, let's have a look now at the output here. Now notice what's happened to our r squared here. It's now 0.585, which is a huge improvement on the last model. Maybe that's no surprise because we're now modeling our variables more appropriately. And we can see here that all 3 of these variables appear to be somewhat significant. You can see their p-values are much less than 0.01, indicating a strong relationship. Now the big problem with this particular regression as we've run it is that it really is difficult to interpret the coefficients here. How do you interpret, for example, this 1942 coefficient of 1 on odometer? So that means if 1 on odometer goes up by 1 unit, the expected price will go up by $1,942. But what does that really even mean? So it's actually quite difficult. The same could be said for the age variable as well. Which brings us to the concept of logarithms or logs. Now this is potentially a way of dealing with this non-linearity problem that we have, but doing so in a way that leaves the resulting regression a whole lot more interpretable. So what's a logarithm? Well, I'm going to leave a link for you in the description of this video, linking to a separate video where I turn up the nerd factor on the mathematics behind logarithms. But for the purpose of this video, we just need to appreciate that logarithms are a way of scaling skewed data. So for example, the classic base 10 log scale will convert numbers that go from, say, 10 to 100 to 1,000 to 10,000. It converts those numbers to 1, 2, 3, and 4 respectively. So it just means that if you have a very skewed data set where you have a couple of really, really high values, instead of them being 10,000 compared to 10, they're now 4 compared to 1. So it really squishes in the extreme values. Now again, I'll go into more depth in the dedicated logarithm video that I'll post up, but we tend not to use base 10, but we use this thing called base e. Now all we need to know for the purpose of this video really is that e is the natural exponential function, which is just some number. It's 2.718 something, 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 something. So it just means that the natural log, or ln, notice how we use ln here and not log. The natural log of this number is 1. The natural log of this particular number, which just happens to be e squared, is 2. The natural log of e cubed, which happens to be this number here, is 3, etc., etc. It's still a way of squishing data in, of reining in this positive skew, but it just has a different base, no longer base 10, but base e. So going back to our little scatter diagram of price versus odometer, you might notice that there's a clump of odometer readings down the bottom, but as we get higher on the odometer scale, it gets a bit more sparse. So we only have a few observations up towards these higher odometer readings. And if we were to construct a histogram of odometer, you can see in fact that it's heavily skewed to the right. Now, one thing about regression modeling is that we usually like inputting variables that are roughly normally distributed. So we like to see a nice symmetrical distribution that has a nice bell-shaped curve to it. And this certainly doesn't have that. So if we were to use this variable odometer in the regression model, there might be some issues. And we'll deal with those issues in part 5 of this video series. But for the moment, just appreciate that if we were to log the odometer variable, the new distribution looks a bit like this, which looks much more bell-shaped, doesn't it? It's symmetrical, it kind of looks like a normal curve. We've got a little outlier up here, that's okay. But it certainly looks much better. All right, so model 3 is going to be the same as model 2, with the exception of the odometer variable, which is now logged. So let's see what would happen when we run this regression using Microsoft Excel. This becomes our output. The R-squared, again, it goes up a little bit, which is a good sign. And looking at the significance of each of the variables here, age squared, and the log of odometer, you can see that the p-values are all very, very low, indicating these 3 variables are significant. And looking at the estimated equation, we can see that the signs at least match up with what we might expect from those variables. Now, to interpret the coefficient of the log of odometer, we could be really technical about it and say that a 1 unit increase in the natural log of the odometer reading decreases the price by $1,079 on average, holding age constant. But I'm not very happy with that interpretation because what the hell is the natural log of the odometer reading? It's not as if that's really helpful to us in a practical sense. But the wonderful thing about logs is that you can interpret them in a different way, which makes it much more accessible. Here we can say that a 1% increase in the odometer reading increases the price by $10.79. Now, how do we get that? Well, you just divide the coefficient by 100. So technically the coefficient represents the change in price for a 100% change in odometer. But what's maybe more useful to us is to say, well, what happens if odometer goes up by 1%? So then we can just divide that by 100 and say, well, it's a $10.79 increase if the odometer goes up by 1%. And this is just a great property of logs, which I go into a bit more depth in the video linked below. But you might not need to go into that much depth if you're just approaching this from a practical standpoint. And remember, the added benefit of all this is that the log of odometer has a nice bell-shaped curve about it, and it's symmetrical as well. So this will help us with our assumptions surrounding regression, which we will meet in video 5. Now, is there anything else we can log in this regression equation? Well, let's leave age as they are at the moment, but maybe let's re-inspect our y variable price. Here's a histogram of the price variable. So a lot of cars are selling for less than $5,000. And again, you get this real positive skew to our data set. We've got a couple of cars that are selling for very high amounts of money, used cars, but most of them are quite cheap. So maybe we can take the log of price. And here's the histogram of the log of price. You can see I've got ln price, the natural log of price. And again, it looks a little bit better. It's nice and symmetrical. One might argue that it's not a classic bell curve, but it's certainly an improvement over the non-logged version. So let's, from here, create model 4 then, where we actually take the log of the y variable as well. So it's the same as the previous model, except we're logging the y variable in addition to odometer. And let's bung this into Excel and see what it provides us. In our previous model, the intercept was something like 11,000 or something, and now the intercept is 9. Similarly, these coefficients are much, much lower. But that's to be expected because our y variable itself, our dependent variable, is actually the log of price now. It's no longer just price. So these represent the effect of each of these variables on the log of price, which is on a much smaller scale so that these coefficients need not be as large. Now, I'm sure some of you watching will have noticed that our r-squared has decreased a bit, and you might have the temptation to then say that this model is not as good as the previous one. The previous r-squared was above 0.5, and now we're at 0.362. But just remember that with r-squared, you can't compare models that have different y variables. So our previous model had price, and this now has the log of price. So unfortunately, our R-squareds are not directly comparable, which I guess highlights one of the shortcomings of R-squared. The important thing to remember is that we have corrected some of those heavily skewed variables, price and odometer. That's really important. And to interpret the coefficient of, say, the log of odometer, it's a little bit different because our y variable is different. So here we can say that a 1% increase in the odometer reading decreases the price by 0.197%, on average, holding age constant. So notice that because the y and x variables are logged, the interpretation of the coefficient is expressed in terms of percentage on both sides. And you don't have to worry about multiplying or dividing by 100 in this case, because you can just say a 1% increase in odometer gives you a 0.19% decrease, because that's negative, in the price. And of course, we have to hold the other variables constant for that interpretation. That's the end of part A. I'll see you after coffee and a biscuit for part B.